Hello and welcome to Digital Systems with Liviu. In this video we are going to talk about decoder and encoder. Decoder. The decoder decodes n input bits into 2 to the power of n output lines. Let's take an example of a 3 to 8 decoder. You can see that there are 3 input lines and 8 output lines, which is 2 to the power of 3. If we look at the truth table, we can see the behavior of this component. 3 input lines, and the outputs are D0 to D7, which are asserted according to the binary number at the input. For example, for 0, 0, 0, which denotes the binary number 0, D0 is asserted. For 1, 0, 0, which denotes the binary number 4, D4 is asserted. If we try to figure out the equations, this will be in this format. D0 is x bar, y bar, z bar, which reflects the minterm M0. D1 is x bar, y bar, z, denoting the minterm M1. In a similar manner, all the D's, we can extract the equations. D7 would be x, y, z, which stands for M7. If we summarize this, the D's equations represent the appropriate minterms. A decoder can be used to implement combinational logic. Let's look at a task. Our task is to implement a full adder with a decoder and OR gates. So, a reminder of a full adder, as we've seen in previous videos, it contains 2 equations, one for S sum, the other C carry. These are the equations, but if we put them in a sigma format, then it would be S is a sigma of M1, M2, M4 and M7. In a similar manner, C is a sigma of M3, 5, 6 and 7. So if we try to implement it using a decoder in which the outputs stand for M0, M1, etc. So in order to generate the equation of S, we have to connect the corresponding minterms to the OR gate which generates the S. Therefore, we have to connect M1, M2, M4 and M7 into an OR gate which implements the sigma function to generate the S. In a similar manner, we can do the C equation by connecting 3, 5, 6 and 7 wires into the C OR gate. Another usage of a decoder can be within a CPU. It is used to decode an instruction with the register code. I've chosen to demonstrate this using the Intel 8051 processor, which is an old processor from the 80s, but it's good enough for the demo. This is a coding of a certain command. The first line stands for the opcode of the command of the assembly command, while the 3 bits on the right denote a register code according to the table on the right. Each register used in this processor has a certain 3-digit code. A stands for 111, B could be 000, etc. So in this example, I've chosen to use a coding of the E register, which is 011. So in order to decode it inside the processor, these 3 lines are connected to a 3 to 8 decoder. So in this example, if the decoder receives 011 as an input, it will assert the line D3, which is the appropriate index of the binary number 0, 1, 1. This line is straightly connected to register E. Therefore, it will activate register E. In a similar manner, the other lines are connected to the appropriate registers corresponding the code that's in the table above. Encoder. An encoder is the opposite of a decoder. For 2 to the power of n input lines, we have n output lines. For a 8 to 3 decoder, we have 8 input lines, D0 to D7, and 3 output lines. The truth table demonstrates the behavior of this element. If we assert the D3 in the input line, we get in the output the index of D3, which is 3. Binary 3 is 0, 1, 1. Now if we try to derive the equations of the outputs, it would be like we learned in previous videos. If we want to derive the equation of x, we have to circle all the ones in the column and then extract all the corresponding minterms. Then x stands for D4 or D5 or D6 or D7. In a similar manner, we extract the equations of y and z for an encoder, 8 to 3 encoder. A special type of encoder is a priority encoder. In a normal encoder, which we saw in the last slide, only one input line can be active at a time. So what if we want to use something which enables more than one active input line at a time? In this case, we have to use a different type of encoder, which is called a priority encoder, which behaves like this. It has 4 inputs in this example and 2 outputs, 4 to 2, but the inputs are arranged in a priority order. The one on the left, the D0, is the lowest priority input, while the D3 is the highest priority index. So for example, if we assert D2 line, we could assert the D1 and the D0 as well, but it doesn't matter because the highest priority is D2, and this is what concerns this priority encoder. Therefore, the output would be the highest priority active, which is 1, 0, binary 2. Now, there is another issue regarding this encoder. What if there is no active line at all? This could happen in this special type of encoder, which cannot happen in the previous type. So in this case, we see the first row where no input is asserted. Therefore, we don't really care about the output, but we have to indicate this special case. In this case, we have to use an extra line, an extra output line, which is called V, valid line, and it is asserted only when an active input is asserted. When no inputs are active at all, then the V line will be 0. A practical example of a priority encoder would be the handling of hardware events in a PC. Let's look at a normal PC which has a priority encoder of 4 to 2 inside with the appropriate lines, and D3 line is connected to the reset button, D2 is connected to a keyboard button, and D1 is connected to a mouse. So for example, if the user presses 2 buttons at the same time, the reset and the keyboard, what will happen in the priority encoder? If we look at the truth table below, then if D3 is asserted and D2 are asserted, then it would be the last line. The D3 is asserted, then we don't care about the lower priorities. Therefore the outputs would be 1 1 for the encoding, and the V line is also asserted. The 1 1 is saved in a special register, and the V line goes to the operating system, which should handle a hardware event. When the operating system receives the signal for a hardware event, it has to check which event was taken place, and therefore it has to check the special register. It would read event number 3, which stands for reset, and will handle a reset procedure. Lesson summary. So what have we learned today? We learned how a decoder works. It has n input lines and 2 to the power of n output lines. The output line is asserted according to the binary number in the input. We had some decoder examples. One example was to implement a Boolean function using a decoder and OR gates. The other was a demonstration of a decode register inside a CPU. Later we learn how an encoder works. It works the opposite way. It has 2 to the power of n inputs and n outputs, which encode the number, the index of the input line. We learned about a specific type of encoder which is called priority encoder, in which the high priority is output in the outputs while the lower priorities are ignored. And then we saw an example of a priority encoder usage inside a PC.